All right. Hi. It's our last class before break. What I actually want to talk about today is vector fields. I actually showed you this earlier in the semester a little bit. No, that's not what I want. Let me just show you some random. Ooh, this is exciting. Hold on. Yeah, so, oh, I have to actually share screen, don't I? Yeah, so there's this vector field applet I showed you briefly last time, and this is actually going to be one of the main things we're going to look at for the last part of the course here, vector fields. We live in a vector field right now. We might live in multiple vector fields, but there's one very famous vector field we live in. Gravity. We live in a gravitational. There's all these invisible arrows in this room pointing straight down, right? You just don't see them, but they're all there pointing down, pushing us to the ground. So there's all these forces, any sort of force. There's magnetic fields and electric fields and stuff like that too. So yeah, they're kind of everywhere. It's sort of a physicsy thing, but we can think about vector fields all over the place. I'm gonna just write on the board a little bit to show you, just to talk about general vector fields. And then I'll just show you a bunch of stuff in this applet, which is kind of fun. But let me just talk about vector fields in general a little bit first. So, so the vector field that we've already seen is the gradient, right? So, all right, this is vector fields. Yeah, so we've seen, given a function f, let's just say f, a function of two variables, we've seen the gradient this upside down triangle f, which is right, it's actually at every point x comma y, it's the partial x derivative times I plus the partial y derivative times j, right? So for example, I don't know, I think a function we had was x squared plus xy. And then that meant that the gradient of f at any point x comma y was 2x plus y I plus, I think, x times j. Is that right? I just take the partial derivatives there. And so at each point we got an error. At each point we get a vector. At each point x comma y, we get a vector. So just for example, I don't know, the gradient at 2 comma 3, we just plug in here, we get 7i plus 2j, right? And so this is a vector field. This is basically anytime you have something that looks like this. This is a 2D vector field. Right? Basically, you have a function times I plus a function times j. So yeah, so more generally, a 2D vector field, we can do the same thing for 3D, is something like, the book I think uses capital F, and I think they use F1 and F2 also. Although a lot of books also use P and Q. which is sort of famous for, maybe I'll use P and Q. I like There's this last thing we're going to do is called Green's theorem, and it's most people know it in terms of this P and Q. So these are both functions where these are both just functions of two variables, right? So these output numbers, but this capital F here with the arrow over it is a vector valued function again. I think I've mentioned this already with parameterized curves. If you put in, we can think of a parameterized curve as a vector valued function of one variable, like we're writing the R with the little arrow over it of t. So this is a vector valued function of two variables. But basically, you get just a point, you get an arrow coming at every point. And so, you can just try to start to draw this. You can sort of like, say we want to draw a vector field. Let's do that example, well, that I have on the screen. So is this one on the screen? It's x squared minus y comma x plus y squared. So sometimes I just list them that way too. X squared minus yi plus x plus y squared j. Yeah, so let's see if we can, what do I mean? Well, what I mean is like, okay, here is the plane, x, y. Let me just mark off a few points here, like, 1, 2. Because these get kind of, so let's say we tried the point like 1, 0. Right, 0, 0 is actually just, there's actually no vector there. It's let's just try like 1, 0, right? What do we get? Whoa, somebody's talking. I like that. I couldn't hear. What happened? Oh, the system said something? Oh. Was it important what it said? Do I need to know? It said record. Oh, that was weird. All right. What if I plug in 1, 0? What do I get here? What vector? Just I plus j, right? Just plugging in 1 and 0 for x and y. So that means that out of this point, there's the vector I plus j. And then we could just start to do this for a bunch of points, right? No, f of 1, 1, f of 2, 1. We could sort of do a bunch of these. And so we get like 4i plus 2j here, right? I think if we plug in there. So now this starts to get a little unwieldy immediately, because now all of a sudden this vector is like that or something. And then we start to get a mess of a picture if we try to start drawing this, because they start overlapping and stuff and hitting each other. Yeah, like what about, like if we tried 1, -1, what do we get? 2i plus 2j, is that right? And so you start to see this thing like, now it's like that, and now it's like overlapping. I guess it shouldn't be parallel actually, but it'll go through this point. Like that, right? And this just starts to look bad, right? It's like, so what we do instead is we tend to, like what vector field applets do, is they tend to scale They sometimes scale everything to the same length and just use like a brightness, like an intensity to represent the length instead. Otherwise, you just get this ugly nonsense, you know? So, but you can sort of see where we're going with this, right? Like, I could keep doing this. This one is actually just 0i plus 2j. So out of this point, we have a vector like that. Let me just do one more. So 2, 1 is, what is that? Is that 3i plus 3j? Check me here. So that's like that or something. So, you know, yeah, so it starts to get kind of a mess because there's also, well, there's no vector here. I guess you can just draw like a point here to be like f of 0, 0 is that. 0, 1 is actually, 0, 1 is interesting. It's minus I plus j. Is that right? So you can just sort of keep going with this. But kind of a mess. Better scale all to a short length. Use brightness or color or something to represent magnitude. So they're all going to point in the right direction. They're just going to be they'll point in the right direction, but they'll all just be scaled so they don't overlap each other. And so if I go back to the screen, and please, if you have questions in the chat, just put them in the chat. If you go back to the screen here, yeah, I'm claiming that this is sort of the right thing, that you might believe. So notice near the center, it's like dark because it's basically like not, the vectors close to the origin are small, like 0. If you plug in 0, 0, you get 0. If I plug in small numbers for x and y, they're still going to be very short vectors. But then they get brighter as you go farther away, and that makes some sense that like x squared plus y, you know, x plus y squared is, these get bigger as x and y get bigger. The ones down here vaguely point in up and to the right, which we saw for at least that one example there. The ones on the x-axis are pointing a little up and to the right. This one's pointing straight. I don't know exactly. There's no scale on here, so I don't know exactly where 1, 0 is. But we're getting something that looks. These look something like at least close, at least in this area here. They look something like. Sorry, there's this little field strength slider I can draw. They look something like the arrows I was drawing. They at least don't violently disagree with the arrows I was drawing on the board. Yes. Okay, so the thing is, right, drawing these by hand kind of sucks, so we don't do that very often. But they are interesting. So, right, so what you can do here, this little app, which is like falstad.com/vector. I don't think I put a link on the handout page yet, sorry. I think I talked about this a little bit before, that like, how do I get to, that if I want to use, some of these are actually like, come from gradients. And when they come from gradients, it actually kind of gives you the surface. Although this is like the negative gradient because it's like going down instead, like the particles like falling instead of going up the surface, they're going down the surface. So I think I mentioned that when we talked about gradients. So there's a lot of these that are like this, but there are other ones that are not. If they don't come from a surface in this applet, if they don't come from a gradient, we're going to talk about that a lot, actually, trying to identify when a vector field comes from a gradient. But when they don't, you can still just plot. You can either plot the vectors, or you can plot, or you can think about what would happen to a particle if this was a velocity field. So at each point, the arrow is basically the velocity of the particle. Or you can think about if it's a force field, which is actually sort of the slightly more natural thing, I think, although it looks less. Right, if it's force, you pick up acceleration. So these things kind of wildly get thrown away. So like, yeah, we'll talk about this. But then there's, so it's just kind of fun to play with this and try different setups. And you can even type in your own. But, and then I also mentioned there's this thing called curl detectors. You're like, what the hell is this? Okay, here, let's add more. These, okay, what are these things? Let me do this versus, there was just a, I wanted a different one. Nope, I wanted the rotational. I thought there was a 1 over r squared rotational in here. Somebody see that? Oh, there it is. What's that? Naturally. Well, okay, so this is the 1 over r versus 1 over r squared. We'll talk about this. It's just, I mean, I'm just trying to show you pictures and introduce you, but like 1 over r is the strength of the field. It's the strength decreases with r, the distance from the origin. So it's like 1 over r. We could see that with, I mean, the vectors show that too to some extent. 1 over r squared is just, it decreases with, by 1 over r squared instead of 1 over the distance squared. So it gets, so notice they're really bright near the origin, but they fade out more as you go away. It's just interesting to think about what the particles do. Whoa. Again, the velocity field's sort of more fun to look at because the particles follow sort of paths a lot of times versus, hard to tell the difference. Just looking, right? I guess it's more violent towards the center. That's 1 over r squared, and even weaker towards the edge. It's hard to tell if these are moving faster than this, but it does seem more violent towards the center. But I do want to look at this thing. We're going to actually talk about this curl detection or curl. So this picture versus, so you got these little jacks, these little crosses with a little dot. I guess just to pay attention if you want to sort of like keep track of something. Can anybody see? Let me do both of them. And there's a difference. There's a difference between what's happening in this one versus the other one. Can anybody tell the difference? Here, I'll go back to the 1 over r. Yeah, are the little crosses spinning? If you follow one of it, is it spinning? It's not spinning, right? This red one here. It's keeping the same, oh, it went away. This one, it's keeping the same orientation, right? Versus this one, it's actually turning, right? This like green one here. That's interesting, okay? May not be obviously interesting, but there's something different there, which is kind of funky. Yeah, here's one. Whoa. Well, first off, let's look at the vectors. So this is y comma 0. So at each point, they're all, do you see why they're all horizontal vectors? Because the y component's always 0 in the vector field, so they're always going to point left or right. And then for y, yeah, I probably should have started drawing a simpler example like this or something. But the bigger y is positive, the stronger it'll point to the right. And the bigger y is negative, the stronger it'll point to the left, right? And then you can see this with, whoa, it's a strong field. It's kind of fun to see. I think it's more fun to see the velocity. You almost think of it like a river or something, right? Force is more like, woo, okay, let's pick up some acceleration. But then curl detection, are these spinning? Oh, is it too many? Do you want me to have like fewer particles? They are spinning, aren't they? Let's look at a saddle. Wait, so this is like, what is this showing me? Do I want the lines? Well, you can see this actually is the like surface. And if I did particles, I think it might switch to the, yeah, it'll switch to the actual surface. So this is the saddle. And if those are particles just like rolling down the surface, well, they're not really rolling, I guess they're rolling maybe force. Oh, because they would roll down and then up the other side and then back and stuff. But if they're just flowing nicely down, then it's like that, right? But if I go to curl detectors, are they curling? Are they rotating? No, they don't seem to be, do they? Don't seem to be rotating. Yeah. What about these? Are these rotating? Yeah, so this is an interesting question, is which ones have curl, which ones have this rotation, and which ones don't? Oh, here's a rotation, linear rotational. So I guess this is actually, if you did the particles, I think they're all sort of rotating at the same, well, I guess they're faster. Are they faster away from the origin? Yeah, let me keep the field strength. So, okay. Constant rotational. This is just where it's a constant. The vector field's constant, but it's sort of, I can actually write down fields for these, and I'll show you in a moment because these are important examples of fields. But let's look at whether this has curl. Does this have curl? Yeah, the constant rotational has curl, right? Did the linear rotational have curl? Wait, that has curl too. Which one didn't have curl? One of them didn't have curl. Was it the one over R? Yeah, that didn't have curl. Okay, let me go back to the board for a minute and sort of write some of this stuff down, just because I think it's kind of strange. In fact, let me do the linear rotational. Yeah, so, all right, let me go back to the board for a second. Okay, so because of this we're kind of just raising questions today. It's kind of the thing, and then after break we'll answer a bunch of these questions. But yeah, like another sort of famous example, if you want, like this linear rotational field. So this is actually the field yi minus xj. If I did that right, it's either that or minus yi plus xj. But if I want to match the picture on the screen, if you start drawing some of these, right, what is it at? Oh, I did do it backwards, I think, if I want to match the one on the screen. So if I go to like 1, 0, then the vector coming out of it is minus, so nothing here, plus 1j. So it's like that. If I go to 0, 1, I get minus 1 plus 0, like that. If I go to negative 1, 0 for x and y, negative 1, 0, and that's a minus j. And if I go to 0, negative 1, that's plus I think, yeah. So it's like that, but they also get stronger as you go out. Like if I did 2, 0, it would be like that. 0, 2. And then if I did stuff at like angles, like 1, 1, I would get minus I plus j, you know. So again, I'm not scaling them to be, I'm actually trying to draw what they would actually look like and stuff like that. But this is a rotational field. This is linear because the think about the magnitude. That's something we're going to think about also sometimes, is like the magnitude of f. Actually, before I say that, just let me remind you that I've used this once or twice before, that like sometimes R is just the position, the vector. We use this just to represent the vector, like the position vector from the origin out to a point. We call it R sometimes, or you could say R of x, y. And then notice what the magnitude of R is. It's the square root of x squared plus y squared, right? Which is also something that we call R, but without a vector, right? Like in polar coordinates and stuff like that, you call R the distance from the origin. And so, yeah, so R is distance from the origin. That's a letter we use for distance from the origin. And then that's why it's a good letter for this vector, because the magnitude is just, the magnitude, you just drop the arrow. And here, if you think about it, what's the magnitude of this? It's the square root of minus y squared plus x squared, which is the square root of x squared plus y squared, which is R. So when it says linear, it's going with, it's growing, the magnitude's growing as R, like R. If you want constant, if I wanted a constant vector field, so constant length vector field, you can think about constant length vector fields. Well, there you have to do, you want the magnitude of f to equal the same, constant. So for example, with this example, yeah, I said this one is called linear rotational vector field. If you want constant rotational, well, you want the magnitude, you want it to do the same rotation stuff, but you want the magnitude to be constant. So how could I do that? How could I achieve that? What if I want it to be magnitude 1? Actually, let me just do it that way. How do we make a vector magnitude 1? What's that? Well, there's the cosine sine thing, but yeah, like how do we make a unit vector from a non-unit vector? Divide by the magnitude, right? So divide by magnitude, yeah. Magnitude. And so here it's so the constant rotational. Well, I'm just using f for everyone, but we would just basically take the one up above and divide by root x squared plus y squared, right? So minus y over root x squared plus y squared, I plus x over root x squared plus y squared j. And you can check that the magnitude of that is 1 always. And so, but actually, there's a little bit of an extra thing you come up with, you pick up there, which is that this vector field is now bad at the origin. You'd be dividing by 0. So if you try the constant rotational, I'm not sure I can actually see it here. Well, the funny thing is it's actually linked 1 everywhere, but then at the origin, there's this like hole but you can't really see it there. But right, and then if you wanted, they talk about the 1 over r rotational. It's more fun with the curl detectors, isn't it? 1 over r would have, that's the magnitude. That's telling you the magnitude. So if we want the magnitude to be 1 over root x squared plus y squared, how would we achieve that? So 1 over r rotational, that means the magnitude is going to be going to equal 1 over r. How would I get that out of these examples? Yeah, right. Because if the magnitude of the original thing is root x squared plus y squared and you divide it by x squared plus y squared, you'd get 1 over root. Good, you get 1 over root x squared plus y squared. Right. So in this case, and you could check. Should we put in parentheses around these? You know, it's that idea that somehow I could pull this out in front. I could just do 1 over x squared plus y squared times the whole thing, right? But if you wanted to check, you could check that like, check. So it's the square root of minus y over x squared plus y squared squared plus x over x squared plus y squared squared. And there's a lot of x squareds plus y squareds, but I could factor that out. Right, and in fact, you get cancellation, and so that's 1 over, yeah. Okay, so there's like different things you can, so it's like ways you can control the magnitude of a vector field. And then if you see right, if we looked at the field vectors, these are strong towards the origin, and you can actually see the hole this time. I guess here, like the field's getting bigger and bigger. When x and y are both really small, the field's really strong, right? And then you can actually see it like blowing up at that point. Okay. So yeah, so this is sort of the idea. It's just sort of fun to try to like, you can do user-defined fields. I guess the other thing I'll say is there's a 3D, here's the 3D version. Yeah. Well, this is a 1 over r squared, but pointing towards the center of space, right? So here, you can kind of see how everything's going. Yeah, and I could have done that in the 2D version. Actually, let me pull up the, oh wait, sorry, I didn't share screen. Yes, you can't see the screen, thank you. Sorry, I just realized it. Where'd it go? Thank you. Yeah, this is the 3D version. If I go back to the 2D version, this one. Yeah, this is like actually like 1 over r squared. Oh, let me do the vectors. This is like the 2D version of this, where you have all the vectors pointing in, directly inward. And the magnitude is 1 over r squared, 1 over the distance squared. You know a field like this. What field behaves like this? Gravity behaves like this, right? This is gravity, is 1 over r squared pointing, I don't know why they say single. What's double? Double, I think, is like 2. It's hard to see there. Let me go back to the 2D. I think this is like, there's 2 sources, and then you have like, it's supposed to be somehow like 2 attractive bodies. So, and that I have no idea how to write that one down, but well, maybe just add 2 vector items. But if we go back to like the 1 over r squared, either here or here. So we could write this down, and we can actually write down gravity. Gravity has a nice, we could write it down as a vector field. We don't usually write it as a vector field. We usually write it as, we just think about, we're at the surface of the Earth, so it's just a constant downward vector of 9.8, magnitude 9.8 meters per second squared. But we could actually use Newton's law of gravitation and write down what it is, right? So, yeah, let me just do that. Sorry, I'm gonna go back to the board. So if we go to 3D vector fields, we're going to have 3 components. We're going to have ij and k components now. And let's think about how you would actually write down an example like gravity. So vector fields. So this would be something like, well, there's 3 functions now. P, sometimes we suppress the x, y, z just to make things. See, I'm going to run out of space. Okay. So sometimes we just write pi plus qj plus rk, just as simple, you know, same that we could on the earlier examples, just pi plus qj. We have 3 functions. Example, gravity. So we can actually think about direction and magnitude, just like we do with any vector. Right now we're thinking about a whole collection of vectors, right? So the direction is straight towards the origin, to the origin. And the magnitude is 1 over the distance squared, right? Okay. Well, let's think about how to write this down. We do have this vector again, this r vector in 3D. I'm just gonna write r equals xi plus yj plus zk. Which way does this point? Directly away, right? Let me just gesture directly away from the origin, right? So I mean, if I'm at a point in space or in the plane, if I'm at a point here, then, you know, it's the vector pointing away from the origin that's the same length as that, you know, those are both sort of, they're supposed to be the same length and point in the same direction. But But those are both sort of R. You can think of R either coming from the origin to that point or from that point going away from the origin, right? So this points directly away from the origin. Points away from the origin. And then, so how do I get a vector field where everything points towards the origin? Negative R. Negative R will go, like I'm at this point, negative R will go right back to the origin, right? So negative R points towards the origin. And we want the magnitude, this is really 1 over R squared, right? We want the magnitude to be 1 over R squared. So the field f of x, y, z equals negative R, which is, I guess, negative x. I just write this way, negative xi plus yj plus ck. That is towards the origin, but the magnitude is R, not 1 over R squared. So how can we fix it to make it magnitude 1 over R squared? We have something magnitude R and we want to be magnitude 1 over R squared. What do we need to divide by? R cubed. So it turns out gravity, so divide by R cubed. So gravity is actually given by the following. It's really just minus R over R cubed, if you want to think of it that way. That's one way people write it down. It's like, it's kind of weird because it's a cube on the bottom, which seems wrong, but it's like, you actually need that to account for the fact that this is not length 1, right? I divide by 1R to get length 1, and then I divide by R squared to get the magnitude to be 1 over R squared. That's what Newton's law of gravitation says, right? And so we could write this out of various different ways, right? Like we could write it out sort of fully. I mean, I could write this as the magnitude of the vector R instead if I wanted to. But yeah, it's kind of neat to see that we can actually write down, like, you know, you can do this for electromagnetism also. I mean, some of that rotational stuff comes from, like, you can think about magnetic fields. Like if you have a current going through a wire, the magnetic field goes. Does the magnetic field go around the wire? So you may know enough physics to know that. Yes, okay. Thank you. Somebody confirm me. So you could say gravity is minus R over, you could write this as the magnitude of R cubed. So it's minus xi plus yj plus zk over, this is the square root of x squared plus y squared plus z squared. So it's x squared plus y squared plus z squared to the 1/2 power cubed. So it's actually 3/2. So it looks kind of strange because it's not kind of what you expect for gravity, but this is actually what it is. And then I could put this in each component if I really wanted to. Yeah. That's right. That's right. Although this is where the direction is kind of easy because it actually is kind of the same as vector. For those rotational ones, there's that little, I did the minus y plus x and stuff like that. But right, so I could write this all out if I really wanted to. Just good to be able to go back and forth among all these different representations. And I'm gonna run out again, maybe. Yeah, so that's kind of what gravity looks like, actually. Okay. Yeah. Trying to think if there's anything else I want to do. Let me share screen again just for fun. So because I do want to preview a little bit what we're going to do after break, just to tell, maybe just talking without writing anything. But there is some cool stuff in here. I'll definitely put a link to this on the handouts page. Sorry, I just don't think I did. The Lorenz tractor. This is a famous. I don't know if you've ever seen the Lorenz tractor. But it's kind of cool. Like if you Google Lorenz tractor, you'll see something like, yeah, it's this butterfly thing. So it actually comes from a system of differential equations. So it's a little bit, oops, where'd that go? Hello, Mr. Butterfly. I don't know what this one is. Hello. What? Streamlines? Oh. Yeah, that's another thing I didn't really show. Like in the Lorenz tractor, if you did the streamlines, you'll probably, well, you can sort of see the things that come from far away get sucked into this little like double loop thing. This is one of the ways that people showed of the chaos that like the butterfly effect. I mean, it's not, it's funny that it's kind of shaped like a butterfly, but like that two particles very close together, if you set them on the same sort of like vector field, that eventually they may end up like very far apart. And that's sort of like sensitive dependence on initial conditions is what that's called. And that's where like chaos theory comes from. And, you know, if a butterfly flaps its wings in Australia, then we get an earthquake here or something, you know, those kind of things. So, so there's lots of interesting things going on here with vector fields. But what we're going to do, oh, and I think actually in the 2D one actually has a line integral. Wait, let me do this. So what we're actually going to do is, let me just do like a random one here. So, yeah. Sorry, I don't know if you can see that. What we're going to do is we're going to ask, well, what if we follow a path in a vector, like we just follow some path in the planar in space, and we think about, we're in this force field, we're in this vector field, and we think of it as a force field, then what kind of work is done by the field? Or what kind of work do we have to do to go against the field or something like that, right? So like here, it's like, it's really that physics concept of work, right? Like if you're like in gravitational field, right? You have to like, if I want to climb the stairs, I'm doing work against the gravitational field. Or if I, you know, if I fall down the stairs, it's the field is doing work on me. So that's positive. So yeah, we're going to call that, if I fall down the stairs, we're going to call that positive work because that's the work the gravitational field is doing on me. If I'm climbing the stairs, we're actually going to call that negative work because I'm going against, it's kind of going against the arrows. Like the gravitational field is doing negative work on me, even though you would think of yourself doing positive work. But hey, we're all self-absorbed. Let's go to like, let's imagine the field's doing. So if you're going against the arrows, you're doing negative work. If you're going with the arrows, you're doing positive work. And all this is doing here is showing you like, I guess this is for closed paths, like, and I think they're counterclockwise paths. It's hard to see probably on the screen, but there's a rectangle here. And it's red here because it's going, I think the paths are always counterclockwise. It's going against the gravitational, it's going against the force field, it's going against the arrows here. When it's going up and down, it's actually going perpendicular to the arrows, so it's not being affected. It's like when we walk around on the same floor, we're not doing any work against or with the gravity field, right? But if I do other, let's see, these are all going to be, if I do this one, this is y squared. So all the vectors point to the right. So now if I do this, you see, and this is counterclockwise path. This stuff up here is in red because I'm going against the arrows, but then I come down here and I follow the arrows, so that's green. And so we're actually going to learn how to compute these. They're going to be integrals, computing the work along a path, like a Like we can have a non-constant force field, and we can have a curvy path in space, and we can actually, as long as we can parameterize the path, which is what all the parameterization stuff is for, we can actually compute the work by, there's an integral we can do to compute that. And that's actually kind of a big topic that's what the line integral stuff we're gonna do starting chapter 18 is. Okay. So yeah, that's a little preview. But you know, play with this. Does this one have curl detectors? Ooh, too strong. Oh, too not strong enough. Curling. Anyways. Okay. All right. Let's stop there. Just a little fun introduction to vector fields. And oh, sorry, somebody did ask a question, but I didn't see it. Oh, but then she said she got it. Okay. All right, thanks everyone. Have a good break. I will email about stuff going on after break soon. Yep, take care. Enjoy your life. You get 10 days away. 9 plus whatever. All right, take care.